Hello everyone, let's dive in. So this is our last unit of the year. I wish we could be doing it together. This is honestly one of my favorite units. It's really interesting how a lot of the things come together. So let's dive in. Right now it's called the normal distribution. More specifically, this is the probability of continuous variables. Last time we looked at discrete variables. Here we're finally going to move on to continuous. All right, to begin, please do try the warm-up. Pause the screen, give it a shot. All right, hopefully you had a chance to do that. Now let's dive in. These are skills we want to keep going throughout your math career. So to begin, write a linear equation that passes through these two and y equals mx plus b slope and point slope. No, y-intercept form. Ugh, you guys know I don't like that, but fine, I'll do it. So first find the slope. Now here we can reduce, so just how far up from this point to this point it goes up 8, and then here to here goes backwards 6. So I get a slope of negative 4/3. I'm plugging in here. If you found another way to get there, that's great. This is fine. But plug in the point slope, remember, just a vertical stretch, some horizontal shift, and some vertical shift using that point there. If I want it in that silly other form over there, I just distribute this slope into both of these. Distribute there. The negatives go positive, and I believe you'll get this 8 and 2/3. Negative 4/3 x 8 and 2/3. All right, write an equation in vector form. In vector form, remember we have a position vector and a direction vector. The common mistake here is people put one vector here, they're like one point here, the other point here. Position, you could use either one of these. I just chose that one. Here we have 8, negative 2. Now remember, your direction vector has to be the vector that connects these two. So I have to ask myself, from here to here, what do I have to do? In the x direction, from 8 to 2, we have to go back 6. So negative 6 there. Here in the y, from negative 2 to 6, we have to go 8. Now you might be asking, can I reduce this? In vectors, you cannot. If it's just algebra, you can because there's not an implied magnitude. Sorry, my puppy's awake. Here, there's an implied magnitude, so you cannot reduce this. Don't reduce it. Leave it right there. All right, question C. Write the equation of a line that is perpendicular to the... Sorry, give me one second. All right, let's see, where were we? Part C here. Find the equation of a perpendicular line. You could do either form. Vector form is probably easier, but point slope is fine as also. So here it wants us to go through point A, so here just put point A in. That little line, I shouldn't have put that there. With pen, I couldn't erase it, but I just put in point A. Again, point A is just 8, negative 2, 8, negative 2. Now for perpendicular, remember we just flip it and change the sign. So here I've flipped this vector, and you only have to change the sign once. And if you forget this, go ahead and just plot it, and you'll see here I've changed the sign. You only have to change it on one of those and flip it. All right, part D. From part A, define this is f of x, and g of x is that boring function. Here, just a little practice with composite functions. If you put 5 into g, well, just equals 2, g only equals 2, and you plug 2 into f. So here we're plugging in 2 into f, and here we actually already know from this point B that if you plug 2 into here, it equals 6, and you can double check that by plugging it into any of these other spots, and it ought to equal 6 over here. Okay, next, if we plug 5 into f, and then plug that into g, well, it doesn't actually matter what f of 5 is because g only spits out 2's. So g of anything is just 2. That's it. Don't overthink those. All right, next, to kind of tie the last unit together, I wanted to give this one a shot. Go ahead and pause the screen. Give it a try. As always, if that felt easy for you, great. Keep going. If you have questions or unsure, hang with me and I'll go over that real quick. And you do see I have answers below, but let me show you how those answers can be reached if you're unclear on how to get those. All right, here for part 1. Find K for the following probability distribution functions. Remember, to be a probability distribution function, it has to add up to 1. So I'm using that property that this all has to add up to 1. These probabilities here have to add up to 1. So I started putting in standard form here. We have k squared plus this, plus this, plus this, and therefore we get this quadratic has to equal 1. Quadratics, we like to set them equal to 0. Most of our tools revolve around that, so just subtract 1 from both sides, and you go here. Now, fractions are kind of annoying, so to make the fractions go away, I multiply everything by 2, multiply everything by 2, you get this quadratic. This is a nice quadratic in that it factors. And so you get these two solutions. K could be 0.5 or -1. We're not going to have a negative probability back over here on our table. Negative probabilities can't exist, so therefore I know -1 is not a valid answer, and K has to be 0.5 then. All right, there's part one. Part A, I mean. Part B, same thing here. We know that this, to be a probability distribution, has to add up to 1. So if I plug in K over 2 times 1, which is right here, K over 2, and then K over 2 times 2, which is 4, and then K over 2 times 3, which is 6. Have this thing, go ahead and solve it. I'd multiply everything by 6 to make these fractions go away. Multiplying by 6 makes most of it go away, but now it's just some simple arithmetic. You get 5.5k equals 6 divided by 5.5, and you get that. Or you could probably also write it as 12 elevenths. That'd be fine too. All right, part C, the expected outcome here. The expected outcome, remember, this is the weighted values idea. So you have this probability of this score, this probability of this score, probability score, probability score. Remember, we multiply all these and add them all up, so it's the sum of the products. Well, 0 times whatever this is 0. 1 times that, 0.2. 2 times 0.5 squared, 0.5 squared, and then 3 times 0.3. That, add all together, you should get 1.6. Okay, let's keep going. I wanted to review distributions real briefly. Hopefully these are easy for you, but if not, no worries. Remember, this is said to have a positive skew here. The skew is this feature right here is kind of stretched out. Negative skew and symmetrical. All right, so earlier in the year when we looked at normal distributions a little bit, now we're going to go a bit deeper. And again, I want to underscore the previous unit was all discrete variables. Those are things that can be counted. Now we're looking at things that cannot be counted. These are continuous variables. These are things that result from measurements. Let me show you some of these. Okay, so here's a big deal slide. Probability density functions in general. So for our discrete variables, it was either 0, 1, 2. There was nothing in between 0 and 1, nothing between 1 and 2, nothing there. So here we had column graphs for that. In this unit now, 8.1 does exist, 8.2 does exist. We could get measurements between 8 and 9. We could probably get a ton of measurements there. So the question is, like over here, we are able to just get these probabilities. How do we get the probability if we have some distribution curve that's telling us the probabilities for various things between two bounds? What does this look like that we've been doing recently? I'm hoping you're thinking, that's integration. That's what integration's for. So here, calculus integration and statistics come together. You need the integration to solve these things. All right, so here's the big definition out of the book that I want to underscore with you all. So here we have some density curve. So here's the big idea. So for a continuous variable x, the probability density function is a function such that for x greater than 0 on its entire domain, so here we have some domain, maybe the only possible values are, whatever, this could be 0 and 100, whatever they are, the entire area under the curve, the integral between a and b has to add up to 1. Same rule as last time, these density functions all have to add up to 1 for area under the curve. Now to find a specific probability, for example, if you want to know the probability between some value c and some value d, or here's the picture, here it is written kind of formal probability notation, probability being between C and D. Well, that's just, we're going to integrate between C and D. All right, so keep that in your mind. Now specifically we're looking at the normal distribution, which we saw a little bit in the fall. A couple quick reminders. So here it's the symmetrical distribution that occurs generally when you have normal things that are being measured. Our mean, median, mode, where would those be? Hopefully you're thinking these are right here, dead center for symmetrical distribution. Then we started looking at these bell curves, kind of the traditional bell curve or a normal curve, and we started looking at from the mean, if you go one standard deviation down or one standard deviation up, well, that's where the concavity changes, another calculus idea. So up into that one, we're concave up, and then between our one standard deviation below, one standard deviation above, we're concave down, and then we go concave back up. Okay, so this function is actually, there's what you would put in your calculator, and we can later on, if we want to get this graph of something that looks like that, that's how we do it. It's this crazy e to the x type function. but some of these things are going to start to mean more and more as we go. Okay, so as usual, this symbol represents the mean, the mu, our variance or standard deviation right here, and so forth. So last time we saw this with the b in the binomial unit. Here, the random variable x is distributed on the normal distribution with some mean and some variance. Okay, let's keep going. All right, a couple characteristics we saw earlier. Hopefully you remember these. Basically, 2/3 is within 1 standard deviation. And then when you got 2 standard deviations, you got 95%. If you got 3 standard deviations, beyond 99%. All right, so just a brief example using these ideas. So the weights of 1-year-old puppies are normally distributed with a mean of 42 pounds and standard deviation of 10 pounds. What's the probability of being between 32 and 52 pounds? Well, hopefully you notice that this is 1 standard deviation below, this is 1 standard deviation above, and so we're just falling into this realm right here. So the probability of that is just these two added together, about 68%. Here, the probability of being between 42 pounds and 62 pounds. The hope is you recognize this is the mean here, so that's right here in the center, and this goes up 2 standard deviations, so that's here would be 52, here would be 62. So to get that, we'd add those two probabilities together. So is that about 47, 48-ish, somewhere in there. All right, roughly 16% of the population will weigh less than what weight? So 16% will weigh less than what weight? We're looking at less than. So if we look at adding this, plus this, plus this, well, that's about 16 when you add those together. So what it's asking is, what is this weight here? If this was 42, go down 1 standard deviation, this is 32. So roughly 16% of the population will weigh less than 32 pounds. Okay, let's keep going. All right, so draw each of the following distributions accurately on one set of axes. Let's give this a shot. I wanted to do this one together. I like to go over some of these together to get the ball rolling. And of course, you can give that a shot first, and then I'll go over it. Okay, let's dive in. So here we have, and it says on one set of axes, and I think that's important. Let's look at why. So here we have a distribution A with some mean and some standard deviation. So let me just draw. I'm going to try and draw a bell curve, a nice symmetrical bell curve that has kind of a changed concavity. That's not great, but it'll do. All right, first I'm going to mark this as 25. Remember, at the standard deviations where our concavity is supposed to change. So here in my terrible picture, this is kind of where the concavity changed, and it was supposed to be right there. So that standard deviation where the concavity changes would be the mean plus standard deviation of 5, so 30. And same thing down here, 20. So there's the first distribution. I'm going to title that A. Now this next distribution on the same axis, here we have a mean of 30 and a standard deviation of 2. So mean of 30, I'm going to mark 30 up here. So the mean, being a symmetrical distribution, is where its maximum is going to be. So this other distribution is going to have a maximum at 30. And standard deviation of 2 means this is a much tighter distribution. It's much more compact. So its peak is actually probably higher than this other one. It's probably higher, and it's a little bit more compact. So as I try and draw this, I know I'm going to go up to 32 and down to 28. I'm trying to have my concavity change at those two values. So I'm actually going to mark that there to kind of guide my work. Try and draw that part, and then start to kind of give it a concave up feature and a concave up feature. Not beautiful, but that'll work. Okay, next let's do this one. Here has a mean of 21, our lowest mean, but our biggest standard deviation. What does that look like? This is a lower, flatter curve. So again, I'm going to mark 21. 21 would be right about here-ish or so. Being more spread out, its peak's probably not quite as high. So I'm going to go lower than this other peak. And again, if this is 21, I know I'm going to go down to 11 for concavity change and up to 31 for concavity change. And at this point, it's getting a little crazy, but the idea has been met. All right, in my last 20 seconds, here are the ones we're going to practice. Go ahead and pause, get those. Here are those first couple of questions, the next couple, and the very last ones. I hope you guys are doing great. Don't hesitate to ask questions. let me help you. That's what I enjoy doing. I'll talk to you all soon.